And that's something you don't get to in calculus until probably your third or fourth year. So what I've tried to do, the way I've put this together, is to say, let's go back to Maxwell's 20 equations, and all we need is 2 of them. And the notation in those 2 will be somewhat familiar to you based on what we talked about. So we'll get to that. So that's the good news. Again, if you look up Maxwell's equations and try to understand it all at once, it's rather opaque. Okay, so before we get to his equations, let's imagine Maxwell tinkering around in his laboratory. So here's a simple circuit with a battery. And it's the battery. And what we have here are, these are 2 metal plates. And when you put them relatively close to each other, they make a capacitor. They become a capacitor. I'm going to show you what that means. That means if Maxwell closes the switch up here to complete the circuit, these electrodes here near the negative pole of the battery are eager to escape if given a chance. And so they're going to flow towards this plate, and then they can't go any further. They're blocked. But what that does is that causes negative charges to build up in excess of positive charges on this plate. So remember, before we close the switch, there's atoms in those metal plates, and there's equal positive and negative charges. It's electrically balanced. But as soon as you throw the switch, electrons, like I say, are eager to flow away from the negative pole of the battery. Well, what does that do? Well, the electrons over here are going to sense they're present and are going to be repulsed. And so they will escape and go over to the positive pole of the battery. And current is currently flowing. But then what happens? Those electrons leave behind some positive charges. These positive charges have been unmasked, so to speak. And as a result, it creates an electric field. And here I've drawn some lines to indicate the electric field. By convention, the vectors always point from positive to negative. And after a short period of time, this plate will become saturated, so to speak, with electric charge. It reaches a saturation state, and no more electrons can fit in. It reaches its capacity. That's why I call it a capacitor. So it's reached its capacity, current stops, and it just remains in this state with a static electric field. Now, can you see electric field? No, of course not. How do you know it's there? Well, Maxwell would say, well, what you do is you put a positive charge, if you prefer, put a little particle here with a positive charge, and of course it's going to feel a force, and it's going to be accelerated towards the negative plate. Moreover, if you put that positive charge out here, there's still some field lines out here, and there's this vector here pushing on the particle, and this vector here pulling on the particle. And when you add those 2 vectors together, more or less, you get a composite vector pointing straight down. And if you go out a little further, you still see some field lines, but they get weaker and weaker. So that's the static situation with what we call direct current. And now Maxwell's going to do something much more interesting. He's going to connect the capacitor to a source of alternating voltage, just like you get out of your wall socket. So the current flows one way, and then it reverses course and flows the other way in a nice undulating shift back and forth. And so the electric field, as the current oscillates, the electric field oscillates. So here it is at, let's say, maximum strength. And then a little bit later, it's moderately of moderate strength. And then it's neutral. And then it shifts and starts going the other way. And then it becomes full strength going the opposite way. So I think you'll see what I'm getting at. If we selected certain time points out of this process and graph them, it would look like this. Oops. Oh, yeah. So we're going to look at the electric field at just one point. It would be the same. It doesn't matter which point I choose, but if you select a point there, this is the time axis. So I'm just showing you snapshots in time, and you can see how the electric field varies over time. The y-axis is E, the strength of the field at that point. And so instead of showing you snapshots in time, if I showed you a continuous graph, it would be a sine wave. So here we go again with sine waves, right? Now recall that the electric field extends beyond the capacitor. But now that we have an alternating current, alternating fields, now Maxwell knows there's much more to the story than what we saw earlier. He knows that a changing electric field generates a changing magnetic field perpendicular to it. This is from his equations based on the work of others before him. And he knows that that changing magnetic field induces a changing electric field. So there's this reciprocal interaction. And so he says, what if this process produces a self-propagating electromagnetic wave of some sort? Well, what do you know? He's right. This is what happens. So he's produced an electromagnetic wave, and I've put in some coordinates. So it's moving in the x direction this way, and the electric field is shown on the z-axis, and the y-axis shows you the magnetic field. So they're perpendicular to each other, and we say they're in phase. And we say they're in phase because the nodes of both waves, the nodes of the 0 points, occur at the same moment in time or the same place in space, always. So it's in phase. Okay, so now we're getting somewhere. So what we're going to do is we're imagining this this wave sort of shooting out the side of the capacitor in more or less one dimension, the x dimension, and it's remember we talked about sound waves, and I had you imagine the sound waves, the pressure waves going through a tube. Well, you can imagine that here, and we're going to look at the wave along a single dimension within that tube. And as you expect, here's the sine wave. Again, y-axis is not a spatial dimension; it's the amplitude of the electric field. And then we have one spatial dimension, x. And if I showed you the B field, it would be along the y-axis, but it would look basically the same except for amplitudes.
Would you explain? Sorry.
Yeah.
What E and B means?
Well, I'm sorry, right. E stands for electric field. And B stands for a magnetic field. And what's the difference? Well, it goes back to what I said. An electric field, if you put a charged particle in an electric field, it feels a force. And if you put a magnet in a magnetic field, it'll feel a force. So that's just a simple way of defining it. Now go back to two spatial dimensions. This is the two through which this wave is traveling. And so what I've done here is at every point along the x-axis, I've put a number down. That represents the magnitude of the field. And we're just talking about the electric field right now. We don't need to worry about both. Just one at a time is enough. So blue numbers mean it's pointing up. Red numbers means it's pointing down. And the point of this is simply to show you that we're dealing with a plane wave. We talked about plane waves a little bit last time. What is a plane wave again? Just to remind you. That means if you took a slice, if you took a cross section through that tube and you looked at it en face, so to speak, in the YZ plane, in the cross-sectional plane, all the numbers would be the same. The amplitude of the electric field is uniform in cross-section. And that means it's a plane wave. I just want to make that point because if we're going to simplify Maxwell's equations, we have to know why we can simplify them. It's because we're dealing with a plane wave And furthermore, the way we created it, it just has that one frequency. So it's a very simple situation. So here are the two equations that we're going to use. And we only need these two to figure out the behavior of this wave. Okay, so now we go back to calculus notation. But it's very simple. We can express this verbally. We just say the derivative of the E field, the electric field, as a function of x equals the derivative of the B field as a function of time. Okay, now that still sounds a little confusing, but remember, intuitively, that just means the following. It just simply refers to the fact when we take a derivative, we're looking at the little change in the E field as we move from one point on the x-axis to a tiny bit further to the right. Remember, an infinitesimal amount to the right. And we're looking at the change in the E field, which is the same as saying we're simply looking at the slope of this tangent at that point in time. So we have different, so the derivative fluctuates. In fact, it fluctuates like another, like a cosine, if you recall. So this formula simply, when we take a derivative, this is all we mean. So what I also want you to take note of is we're talking about these fields as functions of space and time. And we did that with sound waves. And the wave equation that we use is the same wave equation that one would use for sound waves. And this might look familiar. Remember, pressure of a sound wave, pressure of the air in a sound wave is the sign of this argument, we call it. And the argument contains two terms. It includes the x variable as it relates to wavelength and the time variable as it relates to frequency. And if that sort of jogs your memory, but you're kind of confused by that, you can always go back to the notes from last week. But this is the equation, and if it looks familiar enough to you, that's all we need for today, because I'm going to show you how we use it. What we do, first of all, is simply substitute EZ for P. And so if we want to know the change in EZ as a function of x, we would take the derivative of this. And if you recall, the way we do that, let's see. Oh, yeah, we don't need to, let's not take the derivative just yet, but we will. But we're going to use this equation and take the derivative of it. But before we do that, just a couple of points. Because of the way Maxwell created this wave, it's a plane wave, single frequency going in one dimension. All of these other values are zero. So that's why we get to simplify things. There is no B field in the x direction. It's pointing perpendicular to both x and z. Whereas the E field is perpendicular to y and z. So these are all zero. It makes it much simpler. And so let's put a box around this. We'll come back to it later. The second equation that we need is very similar looking. I'll get to these later, but this is mu naught and epsilon naught. These are just constants, and they're conversion factors, if you will. It allows you to convert the dimensions of this with the dimensions of that, the units, and make the numbers come out right. We'll come back to those. But aside from these constants, it's just now the derivative of b with respect to x equals these constants times the derivative of ez with respect to t. So it's just the sort of the flip side of the above equation. Yeah.
What's the x stands for?
Yeah, as in dx?
Yeah.
Yeah, that's the x dimension. So if you go back, here, we have the x dimension. And there's, yeah, that's the direction it's propagating in. And so if you froze, you have for this to make sense, you have to imagine time is frozen for a moment. And all we have to worry about is what's the value of the wave at each point along the x-axis. And so when x equals 0, e equals 0. And remember, I also showed you that these 0 points have to correspond to when x equals pi or 2 pi. So there's that. That's why you see 2 pi in those equations. It's to convert a raw number to a number that makes sense if you're a sine function. So you know when you're supposed to be 0. Does that kind of answer your question? Yeah.
Yeah. One thing I'm confused about is the differentiation between x and time.
Right.
It seems like x is time, but
in a way it is. Now, see if you remember this part. Last week, what I did was I said, okay, time is frozen here. And how can we show? You almost need a separate graph for time. You'd have to change out x for time, and then it would. But then you're looking at a single point in space. So here we freeze time as though time's not moving. When we look at the graph as a function of time, we have to be looking at one particular point in space. And the way we did that last time was, if you recall, I drew a rectangle here and I said, let's imagine we have a window into the wave at this particular point. And we're going to leave the wave the same, but we're going to move that window that direction. That would be the same as the wave propagating through the window. And that's how I try to help you visualize both at the same time. If the wave, literally we're standing still, but we were in this little window and it was traveling that way, we could have the sense that the wave was traveling through us in time. And what we would see is we wouldn't see, this gets back to relativity. That could be our reference frame, this tiny window. We're living in a little rectangle and we see this wave and we can't see any other part of it in space. All we see is that part of the wave that's right in front of our nose at that moment that's passing through the window. And we would see its value go up and down like this. And we would say, oh, it's varying in time. Well, if I want to graph that, I've got a stopwatch. And if I measure its value at different points in time and then extend the time axis spatially, you would see the wave going up and down in time. Does that make sense? But it is. It's hard to do both at the same moment. So it's a very good question, and these classes are supposed to stimulate us to think conceptually and think abstractly. Believe me, I struggled with this as I'm trying to imagine how to teach this. It forces you to go back and think, okay, how did I get to be able to understand this in an abstract way? So it's what I just explained to you is the process I had to go through to figure out how to teach this. Okay. Talked about this. The next part is, now that we're here, the next part is kind of just fun. The magic comes in. Okay. So what we want to do is we're going to manipulate these two equations algebraically. We're just going to use algebra now, and that's when the magic will pop out. So what I'm going to do is I'm going to take a second order derivative of this and this. We talked about that, remember, last time. Remember we said that velocity is the derivative of position. You can watch something change position, and its velocity is the derivative of position, as a car going down the road. Acceleration is the derivative of velocity. It's the rate of change of velocity. But you could also say that acceleration is the second derivative of position. That's all it is. So we're going to take a second order derivative now. We're going to take the derivative with respect to x of both sides. So just when you do something in algebra, as long as you do the same thing to one side of the equation that you do to the other side, the equality still holds true. So that's what this looks like. I'm taking the derivative with respect to x of this and of this. So the equal sign is still valid. And I'm just going to write this a little differently. We kind of introduced this notation before. So the second derivative of e with respect to x is here. This is kind of a combined or a hybrid second order derivative. You take the derivative with respect to x first, and then with respect to t. Remember, when you're dealing with sine waves and cosine waves, without understanding the proof of this, there's some simple rules that allow you to quote unquote take the derivative, meaning to find the rate of change. So we'll apply those rules in a minute. But this is the equation we want to use here. Oh, I've reversed the dt and the dx. You'll see why in a minute, but you can do that. It just means you take the derivative with respect to time first. You apply that rule first, and then you apply the rule for taking the derivative with respect to x. The end result is the same. So it's like they're commutative. All right. Well, let's do the same thing with this equation, except we'll take the derivative with respect to time of both sides. And it just looks like this. These are constants, so they don't change when you take a derivative. That's one feature of them being constants. So we're just going to take the derivative with respect to time, this and this. When we do that, we can write it this way. And so now look, by doing this manipulation, I now have a term on this side that's exactly the same as it is over here. What does that allow us to do? We can substitute this for this. And we've gotten rid of the B field completely. That's going to simplify things. It's an algebra trick, not a calculus trick. So here we go. There we go. All right. Is everybody okay with this so far? I know if it's unfamiliar to you, but and that's okay. I think you can still get the sense that once you have these, they're called differential equations, you can do some manipulation that's in a sense purely abstract, although you can go back and remember what does it mean? Oh, it means it's the slope of this, and that's the slope of that. But something's going to pop out here in a minute that's just sort of made a light bulb go on in Maxwell's mind. Okay, so we've got this equation. So let's go ahead and take the derivative with respect to x of ez. So here's the rule. When you take a second derivative, you take, with respect to x, you take this coefficient of x here, 2 pi over lambda, and you square it. Just a rule. We don't need to question why that rule works, but you square it. And then you make that the coefficient of this sine function, except you make the sine function negative. That's just the rule. And then when you take the derivative of ez with respect to t, you take this coefficient in front of the t and you square it. And you also just drag down the constants because they're constants, but there's the square of this coefficient. And then you put in the same negative sine function. So look what we can do now. We've got things that we can cancel out on both sides of the equation. This is where the beauty comes in. You can cancel out the sine functions entirely. They're the same on both sides. And you can cancel out 4 pi squared on both sides. And you're left with 1 over the wavelength squared equals those two constants times the frequency squared. Do a little rearranging. And you get this. And what is wavelength times frequency equal? Speed. Okay, so what should we call the speed? How about C?
How about S?
Yes.
C squared equals 1 over mu naught times epsilon naught. c equals this. This is the speed of, we're not sure if it's light yet. Maxwell would say when he saw this, oh, that must be the speed of an electromagnetic wave. Okay, that's the speed of electromagnetic wave. But now let me tell you what these constants are all about. That's rather important. Let's say you have a bundle of positive charges. We'll call that bundle Q. That's the amount of positive charge you have there. Well, we know that that's going to create an electric field. So here are the field lines. And let's say you have a particle out here. Question, what is the force? This is a charged particle. What is the force that that particle feels? Whether, of course, if it's negative, it's going to be attractive. If it's positive, it's going to be repulsive. But let's just quantify it. The electric field, actually, we're not talking about the force it feels. We're just going to talk about what is the electric field if we measured it at that point, just to keep it simple. Electric field equals 1 over 4 pi epsilon naught. That's a constant. And then it's the variables would be Q, the amount of charge, and R divided by R squared. Okay, this is actually sort of contained in one of Maxwell's other equations. And what about, so that's epsilon. You don't need to memorize it. You'll see why it's important in a minute. And these are the units. C stands for Coulomb, that's a unit of charge. N stands for Newton, that's a unit of force. And then N is meter. Now, so we'll say that. Now, here's another thing. If you have current running through the wire, this wire, it will create a magnetic field, as shown. The magnetic field will consist of concentric circles around that wire. And it's perpendicular. And let's say you want to measure, or you want to know the value of the magnetic field at some distance, r, from the wire. Here's the formula. It's that mu naught times I, the magnitude of the current, divided by 2 pi r. Okay, that's just to tell you where these constants come from. But one point is they're simply found experimentally by doing these experiments and say, okay, how would we match up, how would we express B in a way that the force comes out as newtons? You want it to come out as newtons if you're talking about a force. Well, you'd have to have this conversion. Okay, fine. Now, if we multiply these two constants together, that's going to get a number. But before I show you the number, I want you to see what the units are going to be. Because these units look like a mess. But if we look at it this way, it's going to be these units times these units. Well, look, here we get to cancel out Coulomb squared. We get to cancel out the newtons. And we're left with S squared over M squared. Now, what if we took the square root of that? It would be seconds over meters. And what if we took the reciprocal of that? It would be meters over seconds. Well, that's velocity, meters over seconds. Well, when you plug in these numbers and do this, you get 3 times 10 to the 8th meters per second. And Maxwell recognizes that now. This was because remember we did experimentally, they had been honing in on the velocity of light experimentally, just empirically. And he says to himself, wow, that looks like the speed of light. So he says to himself, well, I'll tell you what he said. He said, this is not a coincidence. And he wrote this. The agreement of the agreement of the results seemed to show that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. So this is the first sort of revolutionary concept to come out back in that time. Okay. I'm wondering that. I don't know. Let me go on and then we'll take a little break. Yes, sir.
Share the names of those two constants of nature.
Oh, mu is the thing that looks like a U, and then epsilon.
Right, but
It-
there's a name for them, like the permittivity of.
Oh, yes, the permittivity and the permeability. Right. Let's see. You tell me which one is which, because I always got confused.
I forget.
Right. One has to do with an electric field, one has to do with a magnetic field. And obviously they chose the name permeability for a reason, but what is permeable to what? And what is permittive to what? I can never really remember that, but it has to do with capacitors and so on and so forth. Anyway, it does have to do with the extension of an electric field through space. And it has to do, because it depends, remember, it's basically helping you figure out the field strength or the force at a particular position in space. So it has to be related to spatial dimension. But it wasn't necessarily something that would say, oh, that must be a constant that would tell you the speed of something. And that's why it's so surprising, I think. Those constants were found experimentally, considering things that were totally or seemingly unrelated to propagation of waves. And yet here they are, they determine the speed of light. So that's a good point. Okay, let me go a little bit farther and then we'll take a short break. So Maxwell and his contemporaries assumed that light was a disturbance in an underlying field or medium. And they thought, let's give that medium a name. We don't know what it is. There's no candidate out there. It's not like, oh, it's air, because light propagates through a vacuum. So it must be something that's even present in a vacuum, like space. And they call it the ether. They called it the ether. And that seems odd to us today, to imagine something that permeates a vacuum. I mean, isn't that a contradiction in and of itself? But they could not accept the fact, they could not accept the idea that a wave could propagate in a vacuum. To them, a wave must have a medium. So they kept insisting that there's an ether out there, even though that seems to contradict the idea of a vacuum. Okay. So scientists set out to find evidence of the ether. And so we're going to, you may have heard of the Michelson-Morley experiment. That's where we're going next. And I'm not going to tell you all the details, but I just want you to understand the concept of what these scientists were doing, the way they thought they could find evidence of the ether. So remember sound waves, and remember the velocity of sound in the medium is a constant. Now, if you're moving relative to the medium, the velocity is going to be different. So that's what they're thinking. They're not thinking velocity is a constant. It depends on your frame of reference. That's how sound waves. So if you're right, let's see, make sure I get this right. Oh, so we can calculate the wavelength if we know the frequency. Remember, we use a musical tone A. So we fix the frequency and the velocity of the constant, so we know what the wavelength is. And the wavelength, again, the point here is with sound waves, the wavelength doesn't change depending on whether you're moving. So here was my little thought experiment to try to convince you of that. These two people are standing at the end of a long dock, and the waves are rolling in to Santa Cruz Beach. And they want to measure the wavelength. So they position themselves such that with their measuring tape, and they have they've synchronized their watches or their stopwatch. And so what they do is they position themselves so that at a particular moment in time, they're both holding the tape measure at the crest of a wave. All right, so tricky thing to do, but it's a thought experiment that you can imagine them doing. And they would find that the wavelength is a certain length, and they could measure the frequency and the velocity, and this equation would work. And now they start running towards the beach, towards the the beach end of the dock. They're not necessarily running as fast as the waves, but they're running. And what they find is, and I think you can imagine this, as long as they're running at the exact same speed and maintain the same distance, they're still going to show that the wavelength, in other words, the distance between crests is the same. So they get the same value for the wavelength, regardless of whether they're moving relative to the wave motion. So the wavelength is constant in every reference frame. But the velocity, the frequency goes down. I mean, it's logically inconsistent to say that it doesn't, and the velocity goes down in proportion to that. No change in the wavelength. So that's how things should work with light too, they think. And then remember, we did the skating. The wavelength doesn't change. The velocity goes down, the frequency goes down. Okay, going back to this slide, just showed that a minute ago. I'm leaving out some steps. But again, we got this bottom line result. And if this is constant, if the speed is constant, then, or let me show you the next slide. If this is constant, then it must be the case that if the frequency goes down, the wavelength must increase. That's what Maxwell's equations are saying. If this is truly a constant in every frame of reference. But they couldn't see that. So that brings us to the Michelson-Morley experiment, one of the most famous failed experiments in the history of science. And we'll pick up that story after the break. Okay, let's talk about the ether. Here it is. That's what the ether looks like. A bunch of purple dots. Well, remember we talked about the Earth. The Earth is traveling around the sun. And they said, okay, there's an ether, but we don't know if the ether is moving. Maybe ether is stationary relative to the sun. Although if you think about it, why would that be? Because the sun's traveling through the universe. What is the reference frame of the ether? Well, they don't know. So they just assume that at some point in time, the ether must be moving relative to the Earth. The Earth's going around in a circle. So unless by some magical process, the ether stays in the same reference frame of the Earth, it must be the case that the Earth is moving through the ether, just like it would be moving through atmosphere. Okay. Well, if you say that, again, by Galilean relativity at least, we could also say that the ether is moving past the Earth. And some of them even talked about the ether wind. I love that. Ether wind. Ether wind is cold. So how would that, if the ether's moving through the Earth or around the Earth or past the Earth, how would that affect the speed of light? And the way they looked at it is, well, hard to know, but maybe if we measured the speed of light in two different directions that were perpendicular to each other. So let's measure the speed of light going up and down or side to side. So let's again, this is a thought experiment now. This is not the Michelson-Morley experiment, but I just want to teach you the concept using a thought experiment. So this is an imaginary apparatus that I invented in my imagination. And then I put it on a slide and suddenly it seems like it's real. Here's a light source. And this plate of material is semi-transparent to light. And what it is basically a photodetector. So when the light passes through, it absorbs a few photons. Then we're talking about a light pulse. Again, we're not talking about a constant beat, but a light pulse is transmitted from the source. As it goes through this photodetector, a few photons are absorbed, and the photodetector says, okay, at time 0, the light pulse left. Then it comes to the mirror, and it's reflected back. And again, a few photons are absorbed here, and the photodetector says the total time elapsed is t. It took t amount of time for the little pulse of light to go back. So the velocity c is 2d, twice the distance between the two divided by time. That's a pretty simple device. So now we're going to introduce a convention that will make our lives much easier when we get to special relativity, but even easier right now. We're going to say the speed of light is 1. Well, you can't do that. That's ridiculous. Well, no, it's not. It's just something you're not used to doing. Well, 1 what? Well, 1 anything. It could be 1 light year per year. That's a velocity. Light year is a distance. Well, what distance? Well, it's the distance light travels in a year. So 1 light year per year is, by definition, the speed of light. It could also be 1 light month per month, or 1 light second per second. So let's think in terms of 1 light second per second. That's the speed of light. It's 1. That just makes our lives so much easier. So this value equals 1. And again, this is with no ether. We're not thinking about ether just now, but now we are. Here we are. Here's the ether wind blowing this way. So how does that affect the speed of light? Well, it's like going up river in a current. The velocity of the river or current is going to reduce the measured velocity. Let's call that c prime. This would be c as determined by Maxwell's equations. So c prime is c minus b. And then when it goes back the other way, it's simply c prime. Oh, I'm sorry. In the first case, outward bound, what we really want is t. T1 is the time lapse from here to here. That's just d divided by c minus b. And then back inbound, now c prime is c plus b. T2 is this. So what's the total time? You just add the two together. And then when you do a little algebra, blah, 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 you can do this on your own at home if you want to. But basically, you get this. It's 2d divided by 1 minus v squared. That's the total time. Now, what about if we rotate the apparatus 90 degrees? So now the ether wind is blowing this way. Yeah.
Why is v squared?
Oh, well, that's what I'm saying. You'd have to go back and do the algebra. But what you would do is when you multiply, you want to multiply d here by this denominator, d here by this denominator. That's the numerator. The denominator is 1 minus v times 1 plus v. That's going to be your denominator. And the terms that have a v in them cancel out. And you get 1 minus v squared in the denominator. That's a fair question. We will see v squared from time to time. What about now? How does the ether wind affect or influence the effective velocity of light when the pulse of light is perpendicular to the wind? Well, this might look familiar. This came up before when we were dealing with the aberration of light. Remember when Bradley had to angle his telescope, or you had to angle the tube to catch the raindrops because the wind was blowing the raindrops? So if you want the light pulse to come back and hit the photodetector in more or less the same spot, you actually have to angle your light beam to the right into the ether wind. And then the ether wind will blow it back. And so the yellow photons represent the path that the light beam would take if there was no ether wind, but the resultant is the green photon, the green vector. And this is, again, just the old Pythagorean theorem, which keeps coming up. You can't get rid of the Pythagorean theorem. People have tried, just can't. V squared plus this squared has to equal c squared. it turns out that in order to get there, C prime has to equal the square root. And so you can, this makes sense. This is easy. So if you square this, you get C squared minus B squared. And then you add this plus B squared, well, you're left with C squared, and you take the square root. That's the hypotenuse. That's just the Pythagorean theorem. So that's kind of interesting. It looks sort of similar to our first case, but now it's the square root. But again, let's put in C equals 1. There we go. Now, and then this is T1. This is going the outbound. But in this case, it's the same concept coming back. So it's really just 2 times T1. So the total time is 2D divided by the square root of 1 minus V squared.